Hello everyone. In this video, we are going to talk about camera autofocus. Probably you have seen it and you have used it a lot of times that when you move an object with respect to the camera, you see the object very fast goes out of focus and you get blurry images, blurry edges, right? So for instance, you see something like this when you move it too close or too far away, but immediately you see that your smartphone changes basically the practical focal length of the camera and it goes back sharp again like this, where you can take a good picture. This feature is called autofocus, and you might want to say, well, how does it do the autofocus, right? What is the principle behind it? So there are three ways that you can do autofocus, three major ways that you can do autofocus. The first one, which is the most common one and probably the first one ever used, is based on contrast. Okay, so the good thing about it is it's a passive method, so you don't need to send anything away from the camera. You just look at the picture and try to make the best contrast possible, either over entire image, over a single point, which could be at the center of the image, or over several autofocus points. And you might want to say, well, how would you measure the contrast of the image or the sharpness of the image? And the answer is there are so many different ways. One of the common ways to do it is to use the Laplacian operator. So the Laplacian operator, which is basically measuring abrupt changes in an image in both x and y direction, this is one common way. So you can apply the Laplacian operator over, as I said, the entire image or specific patches in the image, specific points. And if it's a digital image, you can do it by the Laplacian operator and convolve the image by the simple Laplacian basically kernel, right, which is a 3 by 3. There are bigger versions of it as well. Convolve any part of the image, any window, with this kernel and get some response, and then you can, because you get a vector or a matrix, and then you can get basically the norm of it. You can sum it up and you can get a measure of the focal length, the one that you have, and then change the focal length practically. And there are different ways that you can change the focal length depending on the camera, right? So what is the mechanism in that camera? That's a separate story. I don't want to get into depth of that. But depending on whether your camera is SLDR or other types of camera, smartphones and so on, they all have mechanisms for changing the focal length of the camera. Have some motor that basically moves the lenses or sometimes mirrors. So I just added this picture to clarify it, right? So many of them you see here, they have a motor for the lens and they can move it forward or backward and change the focal length. And they have their autofocus sensor, which tells them basically where to go to get the best focal length. Now, the way that it is done, as I said, for each location of the focal length, you are going to calculate your contrast or sharpness metric. In this case, you see it's the norm of the Laplacian operator, which again can be over a single or several points, and then changing the autofocus until you get to the maximum of this metric. Okay, there are so many other ways for calculating the contrast. I have a video on my channel called on the same playlist, image processing computer vision is basic grayscale operations, and I talk about 3-4 different ways that you can calculate the contrast, RMS contrast, the Michelson contrast, and so on. But you can just do it with the Laplacian operator as well. Okay, the goal is to get the sharpest transitions that you can get, because if I go back and show you here, so right now, if you look at your edge, right, and by the way, they are all done on a grayscale image. You don't need to do it on a color, so it works on the intensity of the image. So if you have this edge right now, your edge kind of looks like this, okay, or maybe even this, something like that. But here it's quite crisp. It jumps something like that. So if you calculate derivative or second derivative, this is going to give you a lot bigger number than this one does. Okay, for that reason, your edge detector or your Laplacian metric or anything like that will get maximum value when you have the sharpest, the crispest transition, right? The best edge, and that is exactly where you want your focal length to be set by the motors. So that is the most common technique, as I said. And again, as I said, the sharpness metric can be calculated over entire image globally or over specific points. Okay, so you can center it, you can have several points and so on. So here you see there is a collection here, right, of 9 points. You can have here like I guess 19 points, right? For different cameras, there are different number of autofocus points, and you can pick them, and that will tell the autofocus mechanism how many points it should calculate these edges. You see here, you're looking at the light intensity over that region, right? Now, some of these points might not give you anything, right? Because when you're looking at that bird against the sky, there is nothing from these guys. There is no edge. They don't contribute, but the ones that fall on the object, they do. Many people just pick the center and they try to keep the object in the center, okay, by moving their camera. And sometimes I'll talk about it. The new ones, they have a continuous autofocus whereby, or they call it AI autofocus, that basically the focal point can move automatically by the mechanism in their smartphones or something and keep the focus on the object. Okay, so that is like the latest and the greatest in this region. So you either go globally, as I said, or a region of interest, and you can get the maximum here. Okay, the best focus. Now here I just want to briefly show you on my cell phone here, right? So if I go to my cell phone, right, which is a simple cell phone, but still it has these features. So when you go to the pictures, okay, you have to change it to the Pro version, okay, because there are other versions of it too. You see, when you're at photo and so on, if you go to the more and then you go to the Pro, okay, the Pro video or the Pro picture is where you can set up your options for autofocus, okay? So you see you have focus, and you see the focus says multi because I picked several points. But if I go back, you see here, I can pick it to be center, I can pick it to be the manual, I manually pick it, or I can do multi, and the multi is gonna pick several points. So let me see if I can show you. I can move this edge a little bit over, and here we go. I want to show you what happens. There we go. You see them, right? You see all of these focal points, all of these, regions of interest, the autofocus point, and you see here, I go back, it goes blurry, then immediately goes sharp again, or I bring it close, look, it went blurry first, now it tries to, again, you see, making the edge sharp. So regardless of where I move it, it tries to autofocus again by using all of those focal points for you. So this is the nature of autofocus. Now, there is another method which is a little bit more recent, but this one is also passive. That's the good thing about it, and so you don't need to send anything from the camera. This is called phase detection autofocus, or PDAF. Now, the way that this one works is this one, the good thing about it is faster than the contrast base. And the way it works is when the beam of light is coming from the object into the camera, it basically splits it into two phase shifted, into two beams, and then creates two images of the object. And they are, of course, there is a phase shift between them because the path of them is a little bit different. So one reaches a little bit faster to the sensor than the other one. So there is a little bit time difference or phase difference between them. So if you look here, so this is a scene right on the top, and this is your camera. And then here is there are different focal length. You see these distances here, they are a little bit different than each other, right? So your lens is moving in this direction if you look at them. And then you see that the light that is coming, it is split into two. So inside your sensor, you're going to get two versions of the picture, one shown in green, one shown in red. And these have phase shifts, right? And that phase shift is a function of this focal length, okay? And also it's a function of the distance between these two lenses. So if your camera focus is exactly correct, actually these two beams will exactly reach the sensor at the proper time. Therefore, they fall onto each other and there will be what we call no defocus. But on the other hand, if it's focused too near or too far, you see that the distance between them, or the phase difference or the defocus between them, gets bigger. So here, the amount of defocus between these two pictures of the scene, D, is related to the practical focal length squared times the phase difference of the images, okay, or the misalignments, and divided by the baseline. So here, baseline is this distance between these sensors, that is D. Delta X is this offset here, okay, that you see. And then you define defocus as F squared delta X over D. So of course, the bigger the delta X, linearly proportional to that, the bigger the defocus. And then of course, it's inversely proportional to the baseline and related to focal length squared. So the goal is to get this focal length change until this delta X or this D goes to what? Goes to 0, and you get them perfectly on the top of each other, perfectly align them. Okay, again, here the goal is to move these two lenses, move further forward or backward until you get them perfectly on the top of each other. And this method works quite a bit faster than the contrast one. So splitting the beam, getting two images and some misalignments, phase difference or defocus, and setting it to 0 by changing F is your second method. And the third method is time of flight, which it can use a LiDAR or ultrasonic. Most of the time in kind of modern ones is a LiDAR system, it's a laser system that you see here, for instance, in the back of iPhones. Some of the iPhones, they have this LiDAR scanner, and they send a light, and the light goes, hits the object, comes back, and gives you a distance from the camera to the object, which is equal to VT over 2. T is the time of flight. For the time it goes to the object and comes back, you have to divide it by 2 to get the correct time and multiply it by the speed of that beam. So if it's a light, it's the speed of a light. If it's an ultrasonic, that's the speed of sound. So it's a simple distance. And now once you know what distance your camera is from the object, guess what? You can look at a lookup table, and based on that lookup table, you can find the best focal length, right? So here, there are lookup tables for this camera where if you have the distance to the object, they tell you what is the focal length that you should set your system so it gets the best focus. Okay, so you go and look at those lookup tables. So this is the third method of autofocus. Now, if we want to briefly compare these three autofocus methods, the contrast detection methods, they are slow, but their accuracy is relatively good, especially if the light is good. So in older mirrorless cameras like Panasonic, and many of the smartphones still use this. I mean, not Apple, but many of them, Sony's, some Canons, they are all still, including my Surface computer here, they are all using mostly still this contrast detection. The good thing is passive. okay, and it's very accurate, but of course it's a little bit slower. The face detection ones are faster and their accuracy is high too. So some new Nikon, Canon, or Sony, and some of the Apple ones are using that, okay? And the time of flight, which the accuracy of it is moderate, and the good thing is very fast because the light travels very fast, and looking at finding a value out of a lookup table is not that hard. Then of course they are very fast. That's the good thing about it. Their accuracy is moderate because the time of flight can be really good if your beam of light exactly hits the object and there is no attenuation of light, no refraction of light or anything like that. Okay, and how good those lookup tables are. So some of the Samsung Galaxy ones, iPhone 12 Pro, and some of the augmented and virtual reality systems, they are using time of flight ones. Okay, so keep that in mind. And by the way, as you saw, I can have my autofocus to be manual, as I showed you on my camera, or I can have it single shot or continuous. So single shot is when you want to take one picture, one single picture, and that is what you do. You take a single shot, and in that single shot, it does the best job. But many of them, as I said now, you see, when I went to my phone, there was a Pro and there was a Video Pro. That video, it tries to autofocus when you are taking a video or several shots. That is what we call continuous autofocus, or they call it AI servo autofocus, AFC. So as the object is getting closer to you or further away, like this case, this dog, it tries to keep the best focus during the motion. So it has to find the object of interest and tries to put those autofocus points on the edges of this object and get you the best, for instance, contrast or anything, and does it very fast. So you can do a real-time autofocus. So continuous autofocus, as I said, is the best thing that is out there. And many of the modern smartphones and so on, they have continuous autofocus. So this is a summary of how autofocus works in different cameras with some simple formulas and explanations. Hopefully the video was useful to you. I'm going to see you in the next lecture. Thank you.